Greetings everyone. The topic of our video today pertains to the universe is becoming increasingly disordered and entropy is expanding. This is the second law of thermodynamics. Yet quantum theory insists that entropy should remain unchanged. Scientists investigated and untangled this seeming paradox. Without further ado, let us commence with our discussion. Even quantum physics obeys the law of entropy. This fundamental rule states that whenever chance events govern a closed system, its disorder grows. Ice crystals melt into water, and a delicate porcelain vase shatters into fragments. Each scenario exemplifies how order collapses into disarray. Mathematics appears to contradict this, though, because in quantum systems, the calculated entropy always stays constant. At first glance, it looks like quantum physics breaks the second law of thermodynamics. However, a research team at TU Wien examined this discrepancy and showed that different forms of entropy are at play. One must define entropy in harmony with quantum principles. If you do so, no contradiction remains, and entropy in a once organized quantum system rises until it reaches a chaotic endpoint. Equating entropy with disorder can be misleading. After all, disorder might be subjective, but mathematics offers precise expressions for entropy. Entropy is a measure of whether a system is in a special, very particular state, in which case the system has low entropy, or whether it is in one of many states that look more or less the same, in which case it has high entropy, explains Prof. Markus Huber from the Institute for Atomic and Subatomic Physics at TU Wien. He provides the example of color-coded balls in a box when shaken. Only a handful of ordered arrangements exist, whereas many configurations are jumbled. From a physical perspective, that progression determines time's arrow. In the past, entropy was lower. The future is where entropy is higher, says Max Lock, TU Wien. But quantum physics faces a snag here. John von Neumann, both mathematician and physicist, demonstrated that if you possess complete knowledge of a quantum system, the so-called von Neumann entropy, then this quantity never alters. One cannot even tell whether time proceeds forward or backward because each moment is equally valid. But this view leaves out something important, says Tom Rivlin, TU Vienna. In quantum physics, you can never actually have full information about a system. We can choose a property of the system that we want to measure, a so-called observable. This can be, for example, the location of a particle or its speed. Quantum theory then tells us the probabilities to obtain different possible measurement results. But according to quantum theory, we can never have full information about the system. Even knowing probabilities leaves the actual measurement outcome uncertain, and this inevitable surprise must factor into entropy. Rather than calculate the von Neumann entropy for the entire quantum state, one can focus on a specific observable and compute Shannon entropy. This type of entropy can evolve over time. You could say that Shannon entropy is a measure of how much information you gain from the measurement, says Florian Mayer, TU Wien. If there is only one possible measurement result that occurs with 100% certainty, then the Shannon entropy is zero. You won't be surprised by the result, you won't learn anything from it. If there are many possible values with similarly large probabilities, then the Shannon entropy is large. By starting with a configuration that exhibits low Shannon entropy and observing how it develops in a closed quantum system, the research team discovered that entropy ascends until it plateaus near a maximum level, just like in conventional thermodynamics. As time marches on, measurement outcomes grow more ambiguous, so each observation brings an increasing element of surprise. Rigorous mathematics confirmed this, and computer models of interacting particles illustrated the result. This shows us that the second law of thermodynamics is also true in a quantum system that is completely isolated from its environment. You just have to ask the right questions and use a suitable definition of entropy, says Markus Huber. If you explore only a hydrogen atom with a handful of electrons, such considerations fade in importance. Yet modern quantum technologies often require describing systems with numerous interacting particles. To describe such many particle systems, it is essential to reconcile quantum theory with thermodynamics, says Markus Huber. That's why we also want to use our basic research to lay the foundation for new quantum technologies. To support our channel's growth and ensure broader awareness, kindly hit the like, share and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.